All right, cadets, let's go through these last two problems, numbers 4 and 5, on your lens work. Okay, so we didn't get to these to class. Some of you might have gotten number 5 done, so I'm going to jump to number 5 first, where we have an object that is 0.5 centimeters high, placed 8.6 in front of a diverging lens. So that was key. The couple that I've seen today, we missed a little bit of that. So taking a look at that work, on number 5, okay, so I'm going to use our whiteboard here. So this is number 5. We have a diverging lens, right? So here's our diverging lens with a focal length of 8, or we don't know the focal length, yes. Focal length is 7.5. So this one will have a negative focal length of 7.5 simply because it's a diverging, right? But that just means they are located here. So we have that type of a lens, and an object that is 0.5 centimeters is placed 8.6 centimeters over here. So that means our object is going to be 8.6 centimeters away, which is further than the 7.5. So object distance is equal to 8.6 centimeters. In the question, we are looking for what is the height of the image. We're also told the height of the object is 0.5 centimeters, or 0.5 centimeters, and that's everything we were given, right? So in order to solve for this, what I'm really looking for, the only equation that contains the HI is that magnification is HI over HO. I'll call this out right now. I think in your notes, I put in a negative sign there. I apologize for that. You're going to get rid of that negative in that equation. Okay, so that with the H's, that should not have a negative. The one that does have a negative is that magnification is negative DI over DO. So what made this problem difficult is it appears that you don't have enough information. So I need HI, I have HO, but I don't have magnification. I can also use this equation. If I have DI and DO, I can find magnification and use it here. But I do not have DI either. I can also look at this equation is if M is equal to both of those, that means that HI over HO equals negative DI over DO. So that's probably the equation that I really want to use. But I don't have DI, so I'm going to add DI to my list of what I need to know over here. And if I can find DI, I should be able to find HI. The equation to find DI is our original lens equation. 1 over F equals 1 over DO plus 1 over DI. So 1 over F minus 1 over DO equals 1 over DI. So a little tricky because it's not as direct, right? There's a lot of steps that we need to do here. We can't just use an equation. So lots of things to do, but there's our thought process. There's where you get 95% of the problem. And now we just have to plug in and plug it into our calculator. So we do know F, we do know DO. So we can plug this in. 1 over negative 7.5 centimeters minus 1 over 8.6 centimeters equals 1 over DI. So for that, I get DI, or this number over here, to be negative 0.2496, and the units will be inverse, equals 1 over DI. So 1 over that number, 96, equals DI. So mathematically in your calculator, remember you're going to type in negative 7.5, hit X to the negative 1 button, minus 8.6, X to the negative 1, hit equals. You should get this decimal, and then you hit the 1 over X button again, and that'll give you the value, which should come out to be negative 4, and those units would be centimeters, equals your image distance. Which makes sense because the negative in an image distance, as we had with our warm-up question today, means that this is virtual, right? And we would expect that with this type of a lens. So if we have a diverging lens, we expect a virtual image, right? So now I'm going to use that up here in this equation. But before I plug that in, I'm going to get the HI by itself. So remember in step 4. So in this problem, you might be using 2 rows of boxes. Not so easy. We're back up to step 2 where we wrote down 3 rather, where we wrote the equation. Step 4, we're going to rearrange the equation and multiply both sides by HO. So HI is going to be negative DI HO all over DO. Or you could have plugged that in up here, right? We could have used this equation here, found magnification, and then said the magnification times HO is equal to HI. Either one is fine. So if I complete it this way and I have HI equals negative 4 centimeters, HO is 0.5 centimeters all over DO, 8.6 centimeters. So one of your centimeters cancel, you end up with units of centimeters, and I get HI to be 0.23 centimeters. Now, we kind of ignore it. We recognize when there's a negative, but we don't really recognize that that came out to be positive. So what that positive means is it is upright, which matches what we should get for this type of a lens. Okay. All right, so that's number 5. Maybe take a screenshot of that, work through it again. If you had trouble with it, that's the best practice that you can do. I'll blow that back up to get to then number 6. Let's take a look at number 6. Oh, sorry, not number 6, going backwards to number 4. So number 4, you have a converging lens, right, being used to take a look at the moon, right? So if we go back to this, we have a person using converging lens that has a focal length of 35 centimeters, right? So the first thing is you have units in centimeters. The diameter of the moon is in meters, and the distance to the Earth, that would be your object, right? So that might have been not quite as direct, but you are basically using a lens that's converging to look at a really far picture of the moon, right? The moon's diameter, we usually think of a diameter being measured in the terms of horizontally across, but the diameter is really HO. That's the height of the object. So in this case, our diameter is 3.48 times 10 to the 6th meters. It is really far away. So the distance, the average radius of the moon, of the orbit, right? It says and its mean distance from the Earth, the average distance, that would be our DO, is our 3.85 times 10 to the 8th meters. Well, you can imagine for this little lens right here, that focal length seems really, really small. And that focal length is 35 centimeters. If that's in meters and that's in meters, I should change that to meters as well. So 35 meters is our focal length. Okay. So I think just the words maybe confuse some people as to, is that object distance? We have distances, but what were those distances measured? So again, the diameter is going to measure the height, right, of the object. The distance the moon is away would be our object distance, and we have focal length. And the question is, what's the diameter of the moon's image on the paper? So what we're really looking for is HI. So if I list these all out again, we're looking for HI. We have the focal length to be 0.35 meters. We have our object distance to be 3.85 times 10 to the 8th meters. And we have our HO to be 3.48 times 10 to the 6th meters. So starting equations would be using the same equation I had earlier, HI over HO equals negative DI over DO. And again, that comes from the idea that magnification is equal to both of those. If they both equal M, they equal each other, right? So that's a third way we can write that equation. Rearranging that equation to get HI by itself, you get negative DI times HO all over DO equals HI. So I have HO, good to go. I have DO, but again, I need DI. So another equation we're going to use here is 1 over F equals 1 over DO plus 1 over DI. So this problem is relevant to what we're going to do in the lab. So as you take a look at your homework, I guess I'll jumping a little bit ahead here, but we're looking at an object that's really, really far away. So look what happens when we're solving for DI here. We have 1 over F minus 1 over DO equals 1 over DI. 1 over 0.35 minus 1 over 3.85 times 10 to the 8th. That's a huge number, right? So you can plug that in your calculator. Again, in your calculator, you type in 35.35 and hit the x to the minus 1 button, minus. Now, to type in scientific notation, we did this from the past, remember? 3.85, hit the EE button, 8, hit the x to the minus 1 button, and that gives you the 1 over x. Then hit equals, okay? That's going to come out to be a very small number, and it actually comes out to be 0.029, but that equals 1 over DI. When you reciprocate that again, you're going to get 0.35 equals DI. And that's in centimeters. I'm sorry, that's in meters, because we switched all of our units to meters, right? But notice it's the same units, same distance as our focal length. Because this number right here, whoops, sorry, you're dividing by such a huge number that actually approaches 0 as compared to this number. So it really has no effect. And what happens in this scenario is an object that is looked at from so far away, the lens, the image will land at the focal point. That's the definition of our focal point. It's where parallel light is going to land. So objects that are really far away, mathematically shows you why you would have the image at the focal point. So using that over here, plugging that in up here, we have our HI equals negative DI positive point. So sorry. DI is 0.35 meters. HO 3.48 times 10 to the 6 meters divided by HO 3.48 times 10 to the 6 meters. So remember to put parentheses around here. You divide the top quantity divided by the bottom, and you get the height of the image to be 0.32 centimeters. So that actually came out to be 0.0032 meters when you plug that in your calculator, which is 30.32 centimeters. So it's going to be a very, very small image on your screen. Comes out negative. It's going to be inverted, but since it's a circle on the moon, you don't realize that what you're looking at on the screen is actually upside down. Okay. All right. So that is number 4 and number 5. Right. So hopefully that helped. Makes a little bit more sense. Highly recommend that you rework both of those problems to get additional help or to make more sense of them now that you have the worked out solutions. All right, Good luck with that work.